Okay, so good evening. Let's start then today's discussion. Mm. So welcome to you all in the fourth week tutorial session on EMI, EMC and signal integrity. So in the last discussion, we discussed about the spectral bound of the clock clock signals. Uh, so we specifically talked about the trapezoidal signal, the spectral bound, and then the effect of rising time and falling time. All those things, effect of ringing on spectral bound, all these things we discussed and we solved the problems on these topics. Today, we will discuss the resolution bandwidth RBW of a spectral and a spectrum analyzer, the radiated emission model, and far field characteristic of a current element, far field of a dipole antenna. Okay. Yeah. So, as we have already discussed that we know what is a spectrum analyzer, right? A spectrum analyzer is an instrument by which we measure the amplitude of the different frequency components, right? So, whenever we want to measure conducted EMI or radiated EMI, so there we want to measure basically the magnitude of the signal. So we do that by spectrum analyzer. We have omega in the x-axis, and here we have the amplitude. Okay. So there are various frequency components, and there are certain limits, some regulations uh, which are specified by FCC CISPA 22. These are the standards, and they have set some limit for frequency components, like in a certain frequency range. So they have specified that this should be the limit of that this particular component. Now, if the magnitude limit is within that band, then it's fine. Then your product is fine, and it has passed the test. But if it exceeds that limit, then there is a problem, and we will have to take some corrective measure so that it can be limited within that specified limit. Okay, it can be reduced. So there are obviously some preventive measures and some corrective measures. Preventive measures we take while we design the PCB. Suppose we are designing some PCB, so while designing we have to take certain measures so that we can avoid these emissions. We can reduce. We cannot completely eliminate, obviously, but we can reduce it. And there are some corrective measures. So there are some filters, EMI filters, common mode and differential mode filters. So we can design them properly so that we can keep these magnitudes within the specified limits. And if still they are not passing the test, then we will have to redesign the components. Okay. So yeah, so that is the instrument, spectrum analyzer, so by which we measure the signals. So we will talk about the resolution bandwidth. What is resolution bandwidth and why it is important? Then the radiated emission model. So I hope you have studied the lecture. So there actually that model is the electric field and magnetic field associated with the radiation model. We will have to find out what is the electric field due to radiation, radiated EMI. Okay, not conducted EMI, specifically for radiated EMI. So what is E, what is H? We can find out. Then far field characteristic. Why far field? Because as we are talking about radiated EMI, so we will have to calculate what is the electric field and what is the magnetic field uh, at a far distance. The when the distance is significant, not the what is the distance? The distance from the source. The distance from the source, which is basically uh, radiating, which is basically is the cause of radiation. So from that, what is the distance? So when we are talking about far field characteristic, then the distance is significant. And then far field of dipole antenna. Okay. Let's see the first question. What is the minimum resolution bandwidth of the spectrum analyzer for the measured frequency range of 30 megahertz to 1 gigahertz according to FCC and CISPAR 22 for the radiated emission case? So this part, this resolution, this has been covered in the lecture also, but still I will just recapitulate to so that you can understand it properly. So we take one window, right? So spectrum analyzer is an instrument, and we need to specify one window through which it will see what are the different components, right? Now you make the window narrower and you can distinguish all the components more precisely. So suppose you have let's say you have one component, suppose here, which is suppose F1, right? And then you have a component here. You have a component here at F2. Okay. So there here is another window. So you see if this much is the resolution, then you can properly see that there here we have one peak. At F1 we are getting a peak, and at F2 also we are getting a peak. So you will understand that at these two frequencies I have these peaks. I am getting these peaks. Okay. But if suppose this is some say 1 kilohertz, say this window is 1 kilohertz, right? This say this window is 1 kilohertz. This is at suppose let's say some uh, maybe at 50 megahertz. Okay, this is just an a hypothetical example I am giving just for making you understand. This is at 50 megahertz, and this is suppose at some 52 megahertz maybe or something. But so they are quite apart. So they are 2 megahertz apart, and your resolution is 1 kilohertz. So this is like fine. You can easily distinguish that at these two frequencies I am getting two peaks. But suppose you are getting one at 50 megahertz, then you are getting a peak over here which is uh, which is very close to 50 megahertz, and that which is like less than the difference is less than 1 kilohertz. Okay, so we will not be able to distinguish between these two peaks, because as your resolution is 1 kilohertz and their difference, these two frequency components, their difference is less than 1 kilohertz, so it will consider them as one on one. Okay, it will not be able to differentiate between these two. So you will also not get to know that there are two different peaks over here. Okay, so the lesser the resolution, it is lower the resolution, it is better. But obviously the computational time will be more, the processing time will be more, because as the resolution is too low, then obviously it will take more time to process the data. But yeah, obviously then it will be more accurate. You will get to know all the different peaks uh, if your resolution is low. Okay. So the resolution is also specified by these international standards FCC and CISPA 22. What are the resolution bandwidth? What should be the minimum resolution bandwidth for radiated emission, and what should be the minimum resolution bandwidth for conducted emission? For radiated emission, the resolution bandwidth is, and the frequency range is 30 megahertz to 1 gigahertz for radiated emission. And the answer is option C, 120 kilohertz, both of them. For both FCC and CISPA 22, the bandwidth is 120 kilohertz. Okay, for radiated emission. And for conducted emission, the frequency range is 150 kilohertz to 30 gigahertz. And for conducted emission also we have a bandwidth, and that is 9 kilohertz for both of them. Okay. So you will have to remember that what is the, so you understand, right, what exactly I am referring to resolution. Resolution is that window, the width of that window, frequency window. So that is the minimum width that it can differentiate. Okay, that is the window in the frequency. So if the two components are situated apart apart from each other and their difference is more than 9 kilohertz, then it will be able to distinguish between them. Otherwise it is not possible. Okay, so if the components are within this window, two components are within this window, it will not be able to differentiate it. Okay, so these are theoretical questions, so you just need to remember. Okay, let's see. A microwave device has two subsystems operating at different clock frequencies. A spectrum analyzer is measuring the radiated emission from this device. If the difference in the measured signal level is 5 dB, then determine the upper bound of the measured signal. Okay. So if there are two signals, okay. So the difference between the two signals is y dB, suppose. This is the difference. Okay, this is the difference between two signals in dB. So that is 5 dB here. Then we can kind of normalize it. How we can normalize it? So suppose there is this signal whose magnitude is x dB, and there is another signal which has some amplitude, and the difference between the two signals is y dB. Okay, so how we can normalize it? We can normalize it like this, 20. So everything is in logarithmic scale here. You understand that whatever we represent, everything we represent in log scale. So it is just a minute. Yeah, sorry for the interruption. So yeah, so we were talking about the uh, normalizing of this quantity. So if there is a YdP difference between two signals, we can write like this. So 10 to the power y by 20, then 10 to the power x minus y by 20 by 10 to the power x by 20. Okay. Sorry, this should be x by 20. And we can take common 10 to the power x by 20. We can take common, and in the denominator also x to the 10 to the power x by 20 is there. So they will cancel each other. Ultimately, we will get 20 log 10 log 10. It will be 1 plus 10 to the power minus y by 20. Okay, so this is the formula. So here the difference in the measured signal level is 5 dB. Y is given, y is equal to 5. Determine the upper bound of the measured signal. So you just calculate this part, okay? So let's calculate 5 by 20, 10 power minus answer plus 1 so into 20. So this is 3.87 dB. 3.87 dB is the answer, option A. Okay. Okay, let's see the next question. Which of the following condition is desirable for peak detector? Okay, so if you have seen the lecture, so you must have seen what is the circuit of a peak detector. The peak detector circuit is something like this. We have a diode. We have a diode. Then we have resistor and we have capacitor. Okay, like this. And here we take the output. This is our, here we have our input signal V in, okay. And here we have the output signal V out. V out. Fine. So this is R, this is C. So suppose our V in is a sinusoidal waveform like this. Okay. So what we will get over here? So you know diode. So there is only one diode. It will only allow to flow for current flow during the positive cycle, right? Because that time only it will get forward biased, and during the negative cycle it will get reverse biased. It will not allow any current to flow, right? So So first it will rise the, because in the positive cycle the capacitor will get charged through the resistor. There will be a RC network. So it will charge, okay, till the peak of the waveform. Then it will retain it, right? Because there is a capacitor, it will retain the charge. Okay, there will be a slight fall. Okay, then again in the negative cycle there it will so there will be no current in the from the input. Then again in the next cycle it will again charge, and like this. So by this we can detect the peak. Okay, peak of the signal. This is called the peak detector, right? So whatever, so from this waveform you can, so this fall will be very small, not very, if you are using a large capacitor this fall will not be very high. So kind of you can approximate it like this. So you will get the peak. Okay, this is the peak. Now for this, the capacitor should get charged very quickly. Capacitor should get charged quickly, and that should happen within this portion. Okay, within this portion. For that, what is the criteria? The criteria is that your time period t, so this is the time period of the input signal, capital T should be much greater than RC. Okay, RC is the time constant of the RC network. If only this criteria is fulfilled, then within this half cycle the capacitor will get charged quickly and it can retain the voltage around the peak. Okay, around the peak it will retain its voltage. Okay, so option E is the correct option. Option A. Okay, so next question. Consider the following statements for Hertzian dipole. So Hertzian dipole, what is Hertzian dipole? So there will be, we consider an infinitesimally small current element, ideal. So this is very small, and this could be the smallest unit which can radiate, which can cause radiated emission. Okay, this is the smallest unit you can imagine. Okay, so this is a dipole. And due to this, we will have to calculate what is the radiated emission at a particular distance, right? So consider the far field. So for the Hertzian dipole, what are the statements? Far field is inversely proportional to the distance of observation. And statement B is far field is directly proportional to the length of the element and inversely proportional to the current. So obviously for any field you know that your field is inversely proportional to the distance. Okay, so this is far field. Sometimes you will find that it could be r square or r cube, so where this is the distance. So but for far field, this is your field is, suppose we are talking about electric field, it is EF for far field, that is proportional to 1 by r, and it is proportional to I, the current, and it is also proportional to dl. Dl is the length of the dipole. Okay, so first statement is true. Second statement is partially true. It is obviously proportional to the length of the element, but it is not inversely proportional to the current. It is proportional to the current, not inversely proportional. Okay, so sorry, this is like the dipole kind of. So only statement A is correct. Only statement A is correct. Okay. So have you guys seen the lecture where this Hertzian dipole and the electric and magnetic field are computed? What is far field, what is near field, all these things were discussed. Have you listened to the lecture videos of this week?
Yes, madam.
Okay, okay. So you could understand, right? Like what they are talking about, what uh, what was taught.
Yes, ma'am. It is a little bit tough, but we understood.
Yeah, yeah. So basically, see, here we are talking about radiated emission, right? That's why we are talking about far field because we will have to calculate the radiation, the amount of radiation at a far away distance. So nearby there will be storage elements, different induction effect, right? So all those effects will come into play. There will be induction, and then there will be some storage systems. But that's why we talk about far field, where we can only segregate uh, the electric field and magnetic field just due to radiation. Okay, so that's why if you just okay, so yeah. So these were the equations. If we just talk about the different components, so this is the radial component. This is the component at in the direction of theta, and this is the component in the direction of phi. So these we are talking in polar form. Okay, not in Cartesian form. These three are the components of the electric field, and H are H theta and H phi. They are the components of magnetic field, right? So whenever we are talking about far field, obviously R will be large. R is the distance of that. Like suppose uh, you have this axis and R. This is some point. Suppose the distance will be high. Okay, obviously because we are talking about far field. Then we can we can safely ignore these terms where we have r square and r cube in denominator because these terms will be very large. Okay, so that's why this component vanishes when we are talking about far field, this radial component, because we have only r square and r cube. But when we are talking about e theta, in that case we have 1 by beta naught r. There is only r. So we can't neglect it. Right. So this part and this part we can neglect, obviously, because of the same reason, but this component we will have to consider. So your E theta will be this much, and obviously this phase term will be there along with that. If I is 0 and the radial and theta component of H is 0, but again when we are talking about the phi component of the magnetic field, we will consider this much for far field. Okay, and this portion. Okay. So determine the electric and magnetic field at a distance of 2000 meter at an angle of 45 degree. The distance they have mentioned 2000 meter. So this is quite large. 2000 meter means 2 kilometer. This is quite large. Okay. And if you just observe over here, the antenna has a total length of 5 centimeter. So the length of the element, we were talking about current element. So the length of the element is 5 centimeter. So that L we were talking about, this is 5 centimeter, which is equal to 0.05 meter. Everything we will convert into SI units. That is convenient. Okay, we will convert into SI unit. Sorry. Okay, then, and the current is 3 ampere. I is I is equal to 3 ampere. What else? Frequency is 1 megahertz. 1 megahertz. And the angle is theta. This is the value of theta, that is 45 degree. Okay. Now what we will have to calculate? We will calculate step by step. Okay. Let's take another slide so that we can do the calculations. Hmm. So we have all this data. Now we will calculate one by one. First, let's calculate lambda naught, which is the wavelength. Okay. So we can calculate it by this 2 pi. Sorry, we are calculating
C by F.
lambda. So yeah, C by F, where C is your velocity of light and F is the operating frequency. So 3 cross. This is 3 cross 10 power 8 meter per second, and F is 1 megahertz. So 10 power 6. Our wavelength will be 300 meter. So you can understand, right? Our wavelength is 300 meter and the length of the element is 5 centimeter, which is much lower than the wavelength, right? That's why we are calling it Hertzian dipole antenna, where where L is much less than lambda. Okay. The length of the element is much lower than the wavelength. What else we will have to calculate? Eta naught, which is equal to mu naught by epsilon naught. Obviously, we know what is mu naught. This is the permeability of free space, and epsilon naught is permittivity, right? So this comes around some 377, like this. You can calculate it by yourself. What else? We have beta naught. That is the phase. Okay, phase factor. This is 2 pi by lambda naught. This is some, okay, 2 pi divided by 300. So this is 0.02094. 0.02094. Okay. Okay. See, now we have got all the components. So we have got I we know DL, we know eta naught, beta naught, sine theta also, then, and R is given, the distance is given, beta naught we have calculated. So now we will have to just calculate this entire thing, right? And remember, they have asked for far field. Okay. So you don't have to consider this term and this term. just this 1 by beta naught r, this term we will have to consider. Okay. So this will be equal to, so current was 3 ampere and DL was 5 centimeter, 0.05, okay. Then 4 pi and eta naught was 377, 77, beta naught square. Beta naught was some point 0.02094, 0.094, okay, 94 square. Then sine theta is sine 45 degree because the angle was given 45 degree, sine 45 degree.
Ma'am, we no need to calculate ER, no? That is also electric field, no?
Yeah, that is ER, but as we are talking about far field, so these here we get R square and R cube terms, which we can neglect for far field because R is too large. That is
If L is
2000 meter.
greater than lambda, then we use ER, no, for calculation.
So if it is near field, if your R and your length,
L
suppose,
is greater than lambda, I think.
so not greater than, but they may be comparable also. Okay. So not exactly, but if they are comparable L and lambda, then you will have to consider this.
So ER is near field, E theta is far field.
Uh, so no, actually all these terms, okay, so all these terms are electric field. So for far field, we are just make far field also. So the actually, if you want to calculate is more accurately, then you will have to consider all the terms. But for ease of calculation, we are neglecting these terms because they will be very. So if you calculate, you will see they are very low. So even if you don't consider them, it is okay. But and for near field, you will have to consider all the terms. So E theta and E phi, they are just the components of E at different directions. Okay. So they are not near field, far field like that. So R is in radial. So you know, right? Like in Cartesian, we have X hat, Y hat, Z hat. So they are the unit vectors in x direction, y direction, and z direction. Like that, in polar coordinate, we have r, theta, and phi. Okay. So they are the components in r direction, in theta direction, and in phi direction.
So
Understood?
in question, if they ask electric field, we need to calculate E theta only, no, madam, not ER, no?
Yeah. So okay, just see this question once. See, electric and magnetic field at a distance of 2000 meter. Okay. So yeah, mostly you will have to calculate the far field one. Okay. But see, if this criteria is not fulfilled, then you will have to calculate this whole thing. Okay. This whole thing. And here we are just considering E theta y because in no other, this is obviously 0. So anyway, you don't have to calculate anything. And for ER, there is no 1 by R term, only R square and R cube. Only in E theta, we have this 1 by beta naught R term. So that's why we are considering E theta. If in ER we would have, there would be this 1 by R term, then ER also we will calculate. But we have only r square and r cube over here, so there is no point of calculating er here. Okay.
Okay, ma'am, understood. Ma'am, actually, can
Understood,
you
sir?
go to that previous slide? You wrote something, no? Uh, another slide. Yes, yes. Actually, I want to take screenshot.
Okay, okay.
Okay, thank you.
Okay, like okay, I think last week I will upload it. Okay. So we were here, right? So J we will have to consider, because if you need the phase angle, then obviously the J you will have to consider. And then again we have 1 by beta naught R. So again beta naught point 0, sorry, just point 0.094, and R is 2000. So multiplied by 2000. Can you calculate it? Can you calculate this and tell what is the value? This whole thing. Did you calculate? What are you getting? Hello? Okay, so I am getting 3.33 into 10 power minus 5 volt per meter. And if we convert it to microvolt per meter, then we have to multiply 10 power 6, and then it will become 33.3 microvolt per meter. Okay. Did you guys calculate? Did you get the same value? Okay, so let's see. We have option A and B, both is showing 33.3 and 33.3. Okay, microvolt per meter. Then we will have to calculate the magnetic magnetic field also. Okay, so these two are same, and both are showing minus 150 degree. But suppose it would have been something different, then you will have to calculate the phase angle also. How we can calculate it? That is also very easy. So you see there is this phase term, right? E to the power minus j beta naught r. This is the phase term. And along with that, we also have a j. J means that is 90 degree. You will just have to add 90 degree. So this is basically just e to the power minus j. What is beta naught r? So beta naught r is 0.02094 times 2000. So 41.88. But remember, this is in radian. This is not in degree. So don't confuse it, because if you just consider it as degree and then add 90 degree, then you will get wrong value. So this is in radian. And what we can do is, in the answer we have in degree. So we will convert it in degree. Okay, but I think no, it is better. Like we will do it finally when we get it. So yeah, so this is one, and then j means so j we can write as e to the power j pi by 2. Okay, e to the power j pi by 2 we can write pi by 2. We will add pi by 2 with this. 2 minus 41.88. So this is my e to the power minus j 40.3. 40.3. Okay. And if you just see what is the, so this is the angle, some 2309.4. 6. So this is, first you convert it to degree. Okay, and then it will be a very large value, some 2300 something, but just that will be some multiplier of 360, and if you just add that, you will get the angle you will get will be minus 150. Okay, so you just do it, you can do it right now. If you don't understand, just ask me. Okay, just calculate this and verify that whether you are also getting minus 150. Okay, so this is the actually we are getting, this is the angle, but if you just simplify it, because there are like many 360-degree cycles, so you just subtract that, and then what is remaining is the angle, that is minus 150 degree. Okay, so that's how you can calculate the phase. Here it is not needed necessary, because in both the options the answer is minus 150. Now let's calculate the magnetic field. For magnetic field also we will calculate in the same way. We have all the values. We have beta naught value, dl, I, all these things we have. Just calculate it. Five, 4, 5. Yeah. So what I am getting is 8.837, 8.837, 10 power minus 8 ampere per meter. Okay. Convert it to microampere. So you will have to multiply with 10 power 6. Then 10 power 2 will be remaining. So this becomes 0.088 microampere per meter. So this option B is the correct option. Okay. So I hope you understood how we are calculating. Okay. Okay, so what is the next question? Determine the average power density. So there is some radiation is happening, some emission. So due to radiation is happening, and there will be a power transfer, right? There will be a power transfer due to radiation, and we can find out what is the average power density is average, and from that, that is watt per meter square. That is power in a unit area, and then if you multiply it by the area, then you will get the power. Okay, so that is S average. It is in picowatt per meter square. The unit is, so this is the S average. Okay, what we will have to do is, this is E cross H star, and we will have to take the real portion, not the imaginary part, the real part. And after all these vector manipulations, these calculations, you will get finally this expression. This is the power density, average power density. Okay. All these expressions, they are coming from electromagnetic theory. If you have, so you may brush up your electromagnetic theory. So all those equations, the vector multiplication, okay, all these things you may need to brush up. See, so DL we know here, DL we know, lambda naught we can calculate, I is given, and theta is given, R is also given. So this is very easy. We will have to take the data from the previous question. So I was 3 ampere. This was 3 ampere. And theta was 45 degree. R was 2000 meter. 2000 meter. Okay. And the DL was the length of the current element. It was 5 centimeter. And lambda we calculate, it was 300 meter. The wavelength, it was 300 meter. Okay. 300 meter. So let's calculate 15 pi 0.05 9 45 square 100 square to 2000 square. So the answer is 1.472 into 10 power minus 12. So directly we can write picowatt per meter square. Okay. Picowatt per meter square. This is option B. Okay, next question. Consider a Hertzian dipole of length 1 centimeter carrying a phasor current of I equal to 10 angle 30 degree. There is a phase angle of the current. Operating at a frequency of 100 megahertz, determine the elevation component of the electric field at a distance of 10 centimeter away from the dipole and at theta equal to 45 degree. Okay. So let's see here. First, we will calculate the lambda. Okay. Lambda naught basically. So that is we know C by F. So C by F here is 100 megahertz. So 3 to 10 power 8 and 100 megahertz means it is 10 power 8. The wavelength is 3 meter, right? Wavelength is 3 meter. Here you see that wavelength earlier was 300 meter, but now it is 3 meter and the dipole length is 1 centimeter. Okay. Determine the elevation component. What is the elevation component? Elevation component is E theta. Okay, E theta. That we will have to calculate at a distance of 10 centimeter away from the dipole. Now you see here we can't assume that it is the far field one. Why? Because the dipole length is 1 centimeter, but the distance at which we will have to calculate the electric field, that is only 10 centimeter. Earlier it was 2000 meter. Now it is 10 centimeter. So you can't assume far field. You will have to consider all the total expression, not only the 1 by r expression, but 1 by r square, 1 by r cube, everything you will have to consider. Okay. So let's just see. So here the first portion is okay, that is common, but earlier we only considered 1 by beta naught r. Here we will also consider 1 by beta naught square r square, 1 by beta naught cube r cube. These terms also we will consider because now the r is 10 centimeter only. So that far field approximation doesn't work here. Okay. Just yeah. Okay. So the same procedure we can follow. Lambda naught and eta naught will be same because this is a constant. This is 377 and then we have beta naught. Beta naught is equal to 2 pi by lambda naught. Pi by lambda naught. Right. 2 pi divided by 3, so 2.094. Okay. Rest of the things are given. I is given, a frequency and length and also the distance theta. These data are given. Okay. So let's just see. What we will do is first we will calculate 1 by beta naught r, then 1 by beta naught square r square, and then this part. Okay. But you will have to be careful because see, there you can't just do algebraic summation. Okay. Here you have j and j over here, and here there is no j. So this will be the real component, and these are the imaginary components. And at outside also you have this phase term. So while calculating, just be careful, segregate the real part and imaginary part, then calculate it. Okay. So 1 by beta naught r by beta naught r is 10 centimeter. So this is 4.77. 4.77. Okay. Then we have 1 by beta naught square r square. You guys can also try to do it simultaneously, so that if I do some calculation mistake, you can correct me. Beta naught square r square. Okay. So where? So this is 22.8. 22.8. 22.8. And finally 1 by beta naught cube r cube. Cube r cube. Okay. What is this? Cube. This is 108.8. Okay. So these terms we have calculated separately. Then this portion, calculate this portion. This portion is I naught was 10, but it has a phase angle also 30 degree. We will have to remember that. Right now we are just calculating the magnitude parts, and DL is 1 centimeter, right? So 0.01 377 to 0.094 square to 45. Okay, fine. Then 4 pi divided by. So this whole portion, this is 9.3. 9.3. So now if we just write it in numbers, we have 9.3 angle 30 degree. Why? Because the current phase angle was 30 degree. 30 degree. 30 degree. Then here we have J 4.77. 0.77 plus 22.8. 22.8 minus J 108.8. Right? This E portion, this we will consider later. Okay. 108.8. Okay. So this and this we can simplify. Both have J. we have finally in 0.3, 30 degree, then 22.8, this is the real part, minus J, 104.03, so just 104, let's take 104, okay. And now we further simplify it, 0.8 square plus 104 square root 106.3. So this is 990. This is after the calculation. Okay, so the magnitude. Simplifying this. And what is the angle? This is 30 degree and this part is tan inverse minus 104 divided by 22.8. Tan inverse divided by 22.8. This is minus 77.63 inside and we have plus 30. So minus 47.63. Okay. Minus 47.63. So till this point, clear 63 degree. Okay, this is the amplitude. This is 990. Okay. So let's see, 991 is there. But we have two options. One is minus 60, one is minus 90. So we will have to calculate the phase also. Okay. So this is the phase, but we also have e to the power minus j beta naught r. This term also we will have to consider. And 0.94 times r was 10 centimeter. So 0.1. Okay. So this is minus 12 degree. If you just simplify beta naught r and convert it to degree, it is coming 12 degree. And here we have uh, minus, hopefully it is correct. Huh? Okay. So this is minus 47.63, right? So minus 47.63. This is minus 59.63. The total angle will be, if you do minus 47.63 minus 12, the total, this part is minus 12 degree. Then the total angle is almost 60 degree, minus 60 degree. Okay. So option A is the correct option. So did you understand? Okay. Okay. So now I will take a 5-minute break. Then we can resume. Okay. Yeah. Okay, so I just want to mention one thing that see here in this problem we considered total the total expression of E theta, not just the 1 by B naught R part, not only this part, right? Now, if you just calculate this portion, this ideal by 4 pi eta naught B naught square sine theta, this is common to all, but just 1 by beta naught R part. So this part, right? And here we had 9.3. Okay, we got 9.3. So 9.3 times 4.77. So this part was only 44.361, right? So you see our magnitude we got 991, but this part is only 44.36. So it is not sufficient if we just calculate this portion. We will have to calculate the whole expression. Okay. So you will have to see carefully like what is the distance and what is whether your what is the distance, obviously what is r. If r is kind of comparable with the element length, okay, so suppose here it was 1 centimeter and r was 10 centimeter, it is not very far away, so that's why we considered the not only the far field portion but the total thing. Okay. Okay, let's see the next question. Compute the ratio E theta by H phi. E theta, the magnitude, the ratio of the magnitude. E theta we already calculated just in the last question. E theta was 991 angle minus 60 degree. Okay. Now calculate H phi. H phi. Okay. So similarly, just like E theta, for H phi also you will consider the whole expression. Okay. Of H phi. So let's see. 1 by beta naught r we have already calculated, no need to calculate again. 1 by beta naught square r square we have also calculated, so no need to calculate again. Just this part we will calculate. So this part we will calculate. This part is 10 into 0.01 into square sine 45 by 4 pi. 4 pi. So this is 0. Sorry, not this portion. 0.0246. 0246. Okay. And inside we have J 4.77. 4.77 plus 22.8. 22.8. Okay. Just find the magnitude. So 23.29 multiplied by 0.0246. So this is 0.573. This is just the magnitude portion, okay? Because the ratio, it is asked the ratio of magnitude, that's why I am just calculating the magnitude. So the ratio will be 991 divided by 0.573. Sorry, this is 0.573. 573. Okay. 1729. Do we have 1729.4? I guess option B is the closest one. We can select this 1724. Okay. Okay. The next question. A Hertzian dipole is radiating in free space. Measured the measured electric field is zero point 0.1 millivolt per meter at a distance of 100 meter away from the antenna. Determine the value of the electric field at a distance of 500 meter if the dipole is operated at a frequency of 10 megahertz. Here we don't have to calculate anything. See, here first the R is given 100 meter, and what is the electric field at 100 meter? 0.1 millivolt per meter. We know that E is inversely proportional to R. Okay. E is inversely proportional to R. If you just consider the far field one, so so at 100 meter, if it is 0.1 millivolt per meter, then at 500 meter, what will be the field? Just divide 5.1 by 5 millivolt per meter. 0.1 by 5 means 0.02 millivolt per meter. Right? This is the electric field at 500 meter, at a distance of 500 meter. So all the other data, they are irrelevant. We don't need these data for this question. Okay. Okay, I think that's all. Today we don't have any more question. So are all the questions clear to you?
To you? Yes, madam.
Okay, okay.
Okay, okay.
Okay, just practice a little bit, because here you will have to do the vector calculation. So just you will have to be a little careful. Don't mix up the real part and imaginary part. Otherwise, the value you will get will be wrong. So in that case, you just have to be a little cautious. Otherwise, I think rest of the things are fine. Okay, okay. Then today, let's conclude today's session. We will meet in the next week. Okay.
Okay, madam. Thank you.
Okay.
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 Ma'am, actually, one more question.
Yeah, sure.
Uh, so have you worked on any grid integration? I mean, vehicle to grid?
Vehicle to grid. Yeah, like I work on EV onboard chargers. So yeah, I have worked on that.
Okay, okay. Actually, we have recently I have done one hardware. So in that we have done FLL. First, we have we have connected input frequency, grid frequency we have taken as the input, grid
Okay.
amplitude and frequency, and we have using sensor we have sensed that, and we sent into some algorithms,
Hmm.
and we are able to take the unit power factor, grid voltage and grid current output.
Okay.
We
Okay.
used space vector modulation.
Okay.
So have you worked on anything like that, like space vector modulation or something like that?
Yeah. So like I have already like actually studied space vector and all, but my converter its working principle is a little different. So have you heard of like unfolding based converters? Three
No,
phase
ma'am.
unfolding. So
No.
basically, in my converter, actually, the AC/DC portion that is switched at 50 hertz. Like 50 hertz means at line frequency, it may be 50 hertz, 60 hertz, whatever is the grid frequency. And the all the control, all the pulse width modulation, those are performed in the DC-DC stage. Okay. So I think like in your space vector modulation, so your first the front end is like this, right? So you have this H bridge like
Yes.
this, voltage source converter basically,
Yes.
right? So
Yes.
here you are doing space vector modulation, and then you have some, I think, are you using any isolated DC-DC stage, or just this portion you have done, this AFE portion?
Actually, we have done bidirectional AC to DC. It's a novel configuration
Okay,
with
okay,
less switches. Actually,
okay,
we are
okay,
about to write one research paper on that.
okay,
Uh,
okay.
so it's a
So
AC to
what
DC
exactly
bidirectional.
is your, like, do you have any doubt, like, in terms of, like, what exactly is your doubt in this
Yeah.
converter?
In your hardware, if you have done previously,
Hmm?
so did you use for the frequency sensing? Did you use DSP, madam, in that digital signal processor for
Yes,
FL?
yes. Yeah,
Oh,
yeah. Okay, for PLL you were asking?
yes, yes.
Okay, okay, huh. Yes, I have
So
used DSP.
okay, okay. Uh, I just want to know if there is any, I mean, new thing that is going on right now in the research for this kind of things.
Yeah,
No.
actually, I mean, now these grid integrated converters are like quite a common research topic nowadays. So, like G2V, V2G operation, then V2H operation, right? And yeah, so this is quite common. Actually, huh, so this is a very broad topic actually. There are many aspects to this topic. So some people are working on topology based research where they are just inventing new topology where there is either some advantage in terms of efficiency or some advantage in terms of volume reduction. So suppose you are reducing the volume of your filters, LC filters, or in the DC side you are reducing the filter size.
Okay.
And or there could be some research in terms of modulation, okay, right, where you can get better control, better reactive power control, better stability, all these things. So like this is a very broad topic, many aspects people are working. There are also aspects like where you can so modular operation. So you just have a one single one converter which can operate in single phase grid, and then you are just kind of connecting with several modules so that you can also operate it in three phase. Like that also
Okay.
people
For
are doing.
single phase module, they're using three modules for each phase.
Yeah, yeah, like that. Yeah. So
Okay.
how is the control? How you can design that? Right.
Okay. Okay. Okay.
Yeah.
Okay, madam.
Okay. Okay. Okay, thank you for joining. We will meet next week.
Yeah, thank you.